So we'll do that. Yeah, it's going. All right. So we're going to do some simulation analysis. We are going to talk about sample size, population mean, population standard deviation, population shape, and because we just did it with proportions, these are going to all be very familiar to you. We're going to talk about when the central limit theorem applies. Just like before, we had a formula. We have a formula for proportions to check to see whether it applies. We have a formula for means to see whether it applies. And then we're going to use all this to perform probability calculations. So I gave you some practice problems to do here. Not that many. So let's do it. So this is one of the things that we're going to get to as an example here. And let me ask you to help me remember something. So one of the activities is going to be around this particular incident. And when we get to it at the next class meeting or the meeting after that, try and remember to remind me to record it, because it would be good to have in the video index, so that people could refer back to it. So if you can remember, that'd be great. So this is a true incident. There was a tour boat called the Ethan Allen, and it had 47 passengers aboard, and it capsized. Capsized means the boat flipped upside down. And I don't know whether anybody died in this accident, but it was a very serious accident. And the question that came up was whether the people that were operating the boat, the tour operators, should they have known that 47 people was too much? And how should they have known that? So you can imagine, I'm sure there was a big lawsuit about it. And, the people who were injured or died, their families, were suing the tour boat operator, saying they should have known about it. And they used statistics to prove their case. Anybody in this group thinking about becoming a lawyer? Ah, good, we got one. That's good. All right. So you will see this, well, quite depending upon the kind of law that you do, but if you do any kind of trial law, this type of stuff is going to come up all the time. People are using statistics to say, nope, you should have known that. Or, yeah. So we're going to discuss this particular example in a bit. Pennies. Everybody know what a penny is? Everybody knows what a penny is? We don't use pennies very much, anymore. Although, yeah, money in general, I mean, I don't know, I haven't used cash since the pandemic started. I mean, like, I'm not going out buying stuff with money. It's so weird, I mean, we keep a certain amount of cash in the house and we keep it in an envelope, but I'm not going to tell you where the envelope is kept. So, but we keep it in an envelope and we write down a date whenever we take some cash out, so we can kind of make sure that all our cash is there. And I looked at it. I mean, like, hadn't taken out any cash in like 4 months. It was like, wow, I can't believe that. So everything's on the credit card. All right, so we're going to ask the question: how long do you think a typical United States penny has been in circulation? So let's get some guesses here. How long do you think a penny has been in circulation? Typical penny. How long has it been in circulation? Somebody make a guess. Yes, I'm ready. I'm ready anytime you are.
5 years.
5 years. Sylvia says 5 years. That was you, Sylvia, right?
Yeah.
Okay, 5 years. Sylvia says 5 years. Anybody less or more than 5 years?
I was thinking like 7.
You're thinking 7 years. Anybody less or more? This is very interesting.
Maybe 10.
Raina goes all the way up to 10, getting bold here. Okay. Oh, this is so interesting.
20.
What?
Oh, sorry. I was thinking like 20 years.
20 years. Alexa says 20 years. So, this is an interesting experiment because in my other stats class, the lowest guess was 20 years. The highest guess was 70 years. But I wonder if it's because the first person who guessed said, in the other class said 50 years. So then everybody kind of adjusts their thinking to be, oh, well, maybe it's really more than what I was thinking. Ah, interesting. That would be an interesting psychological experiment. Anybody taking psych? Yeah. Do you have to put together like an experiment, or did you already do that? Did you already do it? You have to do one coming up?
We already did it. Mr.
already did
Jenkins,
it?
you were one of our subjects.
Oh, well, yeah, I know, but maybe you have another, you know? So what was it about? I don't remember.
It was what was it about? It was like the list thing. Do you remember? Like we gave you the list that you had to memorize.
Yeah. That's right. That's right. I remember. That's right. Okay, right. Well, this would be an interesting experiment. Okay, so we're guessing like right here is our range. Okay, that's a good guess. We'll come back to it. So this is a question that everybody can answer. If I look at different samples of pennies and their average age, would you expect to see more variability when I had samples of 5 pennies or when I had samples of 25 pennies? Where is there going to be more variability? With a sample of 5 or a sample of 25? Isabella.
Okay, I know I got this wrong last time, but I'm gonna say in the sample size of 5.
Why? You're right. Why?
Because like okay, if it were like 25, then it's more likely that they'll like be repeats, or not repeats, but more similar. But since there's only 5, it's more likely that it'll be spread out. I don't know how to explain it, but
Well,
I see it in my head.
The phrase that we use is the larger the sample size, less variability. Smaller sample size, more variability. Make sense? Everybody remember this? Okay, so what the authors did was they went out and they got 1,000 pennies. Now we are calling that 1,000 pennies a population. Okay, so the population is 1,000 pennies, and they collected these a while back in 1999. And here is the summary information for the distribution of ages of the pennies, how long they stayed in circulation. So they made a histogram. This could have just as well been a dot plot. So for example, see, this is 0 years. That means it's in the first year, 1, 2. So 3 years here. Looks like out of the 1,000, they had about 85 pennies that were 3 years old. It looks like at like 16 years, it looks like there might have been like maybe 38 pennies that were 16 years old. You follow what I'm saying here, how this works, the histogram? So the 1,000 pennies had a mean of 12.264 and a standard deviation of 9.613. Okay, and then they also gave us a nice 5-number summary right here. The minimum was 0. The maximum was 59 years. The median was 11, not that far away from the mean, interestingly enough. Q1 was 4 and Q3 was 19. So, not going to use that one. So Brooklyn, how would you describe the shape of this histogram?
Is it the same as it always is, like unimodal and symmetric?
It doesn't look like it to me.
I don't remember the other like names of the
Okay,
shapes.
hang on, you will in a minute. That's good. Okay, Imani, how would you describe the shape of this histogram?
Hello? Can you hear me?
I can hear you now. Yeah, what did you say?
You right?
This is skewed to the right. It is unimodal, right? But it is skewed to the right. Remember, we got the little man, you know, on his snowboard, you know, going down the mountain to the right. Okay, so this is a skewed right distribution. Brooklyn, unimodal and symmetric means it's kind of symmetric. It's kind of even around the middle. But this one, nah, this is not, wherever you put the middle here, it's not really even on both sides. You good with that? Everybody good with that? Okay, so this is a skewed distribution. What are the observational units, Emma?
Is that the age?
No. The variable is the age.
Okay, so the observational unit is like the number of pennies.
Well, it's actually just the pennies.
Okay.
All right, now let's remember the variable describes the observational unit, right? The age describes the pennies. So like if I had like here like 85 pennies that were 3 years old, this number here is not going to change, but from penny to penny, the age does change. Are you okay with that? Everybody remember this? This was a while back, but this is something that keeps popping up. Okay. So Emma, one last thing: is age a quantitative or a categorical variable?
Quantitative?
That is a quantitative variable with no question mark. It's a quantitative variable. Okay. So for quantitative variables, we are going to analyze the mean or the X bar. For categorical, we did the proportion pi or p hat. Okay. The quantitative, we are doing the mean. All right. So, oh, I just gave this one away. So if these pennies are a population, then the mean is represented by, what is that symbol called? Anybody remember?
Mu.
Mu, yeah, like the cow, mu, right? And the standard deviation is represented by the Greek letter sigma. Okay. Does not follow a normal distribution, skewed right. We already did that. All right, so this is a table of all the information about the pennies. You know, I told my other class this story. I'm going to tell you guys this story too. I'm going to tell you a penny story. Wait a second here. Penny story. Any image. All right. Here, this is a good one here. All right. So you see this penny? This is what a penny looks like. And y'all know there's a date on the penny, right? Yeah. And underneath that, there's a letter which indicates where the penny was minted. I don't remember exactly what they are, but that's, you know, that's where the penny was minted. You okay with that? Yeah, so I had a penny when I was a kid. Let's see if I can call it up. 1909 SVDB penny. I still have this penny actually, so here we go. Great, this is a 1909, stop, I don't want you. This is a 1909 S, and on the back of this penny, it has these 3 letters VDB. Can you see that? Yes, this is a 1909 SVDB, and this particular penny is worth almost $900. So it's a very valuable penny. It's like the second most valuable penny if you're a penny collector. And I used to collect pennies. And the way I got this 1909 SVDB was my great grandma had this little bag of change that we had when she died, and we went into it And there was this 1909 SVDB. So it's a very, 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 very valuable penny. So I was with my older neighbor, Stanley Klein. Have I ever told any Stanley Klein stories to this class? Okay, well, you're gonna love this then. Okay, so Stanley Klein. Stanley Klein, a couple years older than me, and we're looking at our coin collections, you know, and I have to go to the bathroom. So I go in the house, I come out, my 1909 SVDB is gone. It's gone from my penny collection. And amazingly enough, who do you think has one now? Stanley Klein, right? But the reason that we knew, or that he knew, that it wasn't mine was because it had a scratch on it. So he had stolen my penny and taken a nail and scratched it so that it wouldn't look like mine. Now, you probably don't know much about penny collecting, but the better condition a penny is in, the more valuable it is. So by putting a scratch on that penny, he basically ruined its value. I mean, just destroyed it, right? You know, and you know, so he got, I mean, it didn't take long to get through that story with his parents, and he got into trouble for that, right? But I got two other good Stanley Klein stories. So again, we're little kids, and you ever have those big giant, like, when I was growing up, they were always purple, but big giant purple suckers, you know, and it'd take like a day and a half to eat it, right? You're licking it, you know, and your mouth is all purple, and they're big giant things. So we're standing out in front of the front yard, and we're eating these suckers, and he looks at his sucker, and he looks at my parents' front window, bam, and he throws the sucker and smashes this window to pieces. Just, you know, insane, right? So then the third story is my mom is out front talking to Helen Klein, which is Stanley's mother. They're having a conversation, and I come running up and I say, "Mom, mom, 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 mom," and she decides that she's going to take this opportunity to teach me not to interrupt. So she says, "Glenn, I'm talking to Helen. Just wait." "But mom, mom, mom," "Glenn, I'm talking to Helen. Just wait." So she talks to Helen, 10, 15 minutes go by, and finally they're done. She turns to me, "Now, Glenn, what is it?" So we had a dog, and the dog had a dog door, right? And I say, "Mom, Stanley Klein took the hose, put it through the dog door, and turned on the water." So the whole kitchen is like completely flooded, you know? So those are some Stanley Klein stories, but the really interesting part. So if you had asked any of Stanley Klein's teachers when he was growing up what he was going to be, they would say he was going to be in prison. You know, and literally they would say that Stanley Klein, he's going to go to prison, right? World famous neurosurgeon. You know, yeah. So, you know, you just never know, you know. So and actually it's kind of funny because you know, my mom went into this assisted living facility, and Stanley Klein, he sent me an email a few months ago and says, you know, "What's your mom's phone number? I'd like to call her up and check in, see how she's doing." Just, you know, as a neighborly kind of a thing, because Helen is long gone. And so I said, "You know, by the way, Stanley, I tell my students these stories about you." So he thought that was pretty funny. Oh, you know what? And I forgot to tell this other class. Maybe I shouldn't tell you this one. No, I'll tell you. He reminded me. He says, "But you didn't tell him about the time that the two of us broke into the school and got arrested by the police." So we broke into our elementary school, just being kids, you know, like writing with chalk or something like that. And the police came, and they like took us down to the station, you know, and our parents had to come collect us. It was really pretty traumatic, you know. So I do not have a record. I do not have a police record for that. We'll leave that hanging right there. So, all right. So yeah, so that's Stanley Klein. So this example always kind of reminds me of the Stanley Klein SVDB story. All right, so 1,000 pennies. What they did was they cataloged every single one of these pennies by how old it was. So here's the table, and the table is like broken into three columns. I'll I'll draw the columns so you can see them a little bit better here. So they gave each penny a number. So like, for example, penny number 102, which is between 101 and 150, was 2 years old. Penny number 880, which is between these numbers, was 24 years old, and there were 19 of them. You follow how this chart works here? Okay, so what we're gonna do is we're gonna do some random stuff. So wait a second here. Okay, so I want you to draw a random sample of 5 pennies, and here's how you do it. So everybody get your calculator. And we did a little bit of random stuff earlier. So if you press the math button and then scroll over to PRB for probability, and you go down to number 5, which is rand int, or you can just click number 5, and then put in 0,999. Those are the numbers of all the pennies. Close your parentheses. And so my first penny is number 166. So 166 is in this group. So my first penny is 3 years old. And then I'm going to do it again. You can just hit enter and it'll do it again. My next penny is number 830. So that's in this group here. My next penny is 22 years old. Okay, so do that for 5 pennies. Everybody do that for 5 pennies. Boy. Not good. Not good. Not good. So everybody got the ages of their 5 pennies? Not yet? Okay. Okay, so I'm going to put my 5 pennies on this dot plot, or kind of close. So I got one that's 3, 22, 0, 6, and 6. So we're going to go through everybody here and put everybody's penny on the dot plot. Okay, so Karina, read me your 5 pennies. Okay.
My first one was 29, then 26,
Mm-hmm.
2,
Mm-hmm.
11,
Mm-hmm.
and 8.
Okay. Alexis, what do you got?
I have 19, 12, 3, 5, and 32.
And 32. Okay. Alexi, what do you got?
I got 5, 8, 22, 26, and 29.
Good. Okay, Abby, what do you got?
I got 26, 21,
7, 11, and 4.
Okay. Isabella,
I got 12, 0, 2, 13, and 22.
22. Okay. Juliana,
I got 29, 10, 2, 11, and 8.
good. Megan,
29, 26, 2, 11, and 8.
8. Okay, good. Here we go. Brooklyn,
I got 34,
34.
45, 56, and 42.
42. Now that seems strange to me. You were reading the age to the left, right? Not to the right?
Mr. Jenkins, I sent you a private chat.
Okay, I'll check it out, Isa.
Wait, was it
So give me one of your, what was one of your random numbers?
34?
A random number was 34?
Yeah.
So that would have been 0 age.
Oh, I forgot that we were doing it on the
You were
okay.
doing the count?
Yeah.
Okay, redo it, redo your thing. And because yeah, those just turned out to be too high. That was improbable. Alondra, what do you got?
I have 3.
What, 30?
3.
3, okay.
And then 4. 16.
Uh-huh.
22.
Uh-huh.
And 28.
28. Okay, good. Okay, Emma, what do you got?
I got 3, 4, 17, 22, and 28.
That's interesting. Isa, the answer is yes. Okay, where are we? Reina, what do we got?
I got 4,
Mm-hmm.
25,
Mm-hmm.
2,
Mm-hmm.
6.
Mm-hmm. Was there one more that I missed at the end?
Oh, 9.
9. Okay. Alondra, what did you get? All right, Alondra disappeared. Brooklyn, redo it.
I got 0, 26, 13,
Uh-huh.
8, and 26 again.
And 26 again. Okay. That makes a little bit more sense to me. Yeah.
Yeah.
Sylvia, did you do it?
Yeah, I got 4,
Uh-huh.
25,
Mm-hmm.
17, 28, and 31.
Wow, interesting. Wow, this is a trip. And Imani. Cannot hear you.
Hello, can you hear
Yeah,
me?
I got you now.
I have 29,
Uh-huh.
26,
2, 11,
Mhm.
and 8.
And 8. Okay, well, this is interesting because I mean, if we'd had more, I would have expected the distribution to look more like that, you know, more skewed. As it is, it's definitely more on this side of the axis. Does everybody agree with that? Right? But actually, I mean, if I look at this distribution right here, it almost looks kind of like bimodal, doesn't it? That's weird. I wonder why that's the case. I'm guessing it's just sampling variability, but we'll figure it out. Okay, so what I want you to do is calculate the mean of your 5 pennies. So if I go back to my 5 pennies here, mine were 3, 22, 0, 6, and 6. So I'm going to go 3 plus 22 plus 0 plus 6 plus 6. And I'm going to divide that by 5 because I have 5 pennies. So my mean was 7.4. And then I'm going to go to this little table right here, and I'm going to write in 7.4. Everybody follow me? Okay, so what you need to do, we're just pushing buttons today, is take 4 more samples of 5 pennies. Okay, so do the same thing we just did 4 more times, and for each sample of 5, take a mean of those 5. You with me? Everybody follow what I'm saying here? Okay, great. Go for it.
Mr. Jenkins, can you go back to the table?
Oh, that'd be a good idea, don't you think?
Thank you.
You mean you didn't memorize it? You didn't memorize the table? Gosh, slacker. Don't take me seriously, please. And how's that? Can you see it? Everybody see it clearly enough? Okay.
Wait, so we're starting with the 5 we already did and
Yes.
finding the mean and then doing it 4 more times?
That's correct.
Okay.
That's right. 4 more times. How we doing? Making progress? Anybody finish? Not yet? Okay, keep going. I just got a new hummingbird picture. I'll send it out. You're so cute. All right, let's see if we can't, yeah. Okay, so I need to, should have done this a minute ago. Let's close this page. Okay, so let's see what we can do now here. All right. If you're not ready, when I get to you, just say you're not ready and I'll come back. So Karina, do you have your 5 means?
Yes.
Rattle them off.
The first one is 15.2,
Uh-huh.
then 13.2,
Uh-huh.
11.8,
Uh-huh.
13,
Uh-huh.
and 9.2.
Good. Okay, Alexis, you ready?
Yeah. Okay. Mine are a lot bigger, so now I'm like kind of questioning if I did it right. But for my first one, I have 14.2, and then I have 76.8.
Nah, mistake.
Yeah, because actually, I got a lot of the same numbers, like higher numbers. So it was like strange because I had a couple of like 24s and like 19s in the same set, and then in my 5th set, I got a mean of 108.8.
Are you remembering to divide by 5?
Yeah, I divided by 5.
But you couldn't because the oldest penny is is 59 years old. So you can't have an average that's higher than that.
I don't know why. I'll redo it and see like where I went wrong, but I don't know why. Like,
Okay,
Picking
are
up so
you
high.
reading the you're not by any chance like adding like the number of the penny, you're looking at the age?
yeah, I'm looking at the age. I don't know why. I even redid a couple of them, but mine are coming out like really high. I only had 2 of them that were like, my first one was 14.2, and then like my 4th one was 16, and those were the only 2 that made the most sense, and then the other ones were too high.
Yeah, they're too high.
Yeah.
Take a look and see if you can figure it out.
Okay.
Okay, Alexi, you have 5 for me?
Let me see. Let's see. I think there's 9.3.
Mm-hmm.
14.1.
Okay.
12
Uh-huh.
and 15
Uh-huh.
and let's see. And the last one is 11.3.
Good. Thank you. Okay, that's good. Okay, Abby, what do you got? Rattle them off quick. I can do it faster.
Okay, I got 7.1,
Uh-huh.
6.8, 5.2,
Uh-huh.
11.3,
Uh-huh.
and 9.5.
Okay, good. Okay, Isabella.
I got 9.8, 9, 14.4,
Uh-huh.
15, and 17.
15, and what was the last one?
17.
17. Okay, Megan.
15.2,
Uh-huh.
13.6, 11.8, 13, and 9.2.
Good. Okay, Alondra.
I got 7.2,
Uh-huh.
5.4,
Uh-huh.
13.4,
Uh-huh.
15.8,
Uh-huh.
and 14.6.
Good. Okay. Brooklyn.
I got 14.6,
Uh-huh.
9.8,
Uh-huh.
11.8,
Uh-huh.
9.6,
Uh-huh.
and 6.
Good. Well, this is working out good. Juliana. Can't hear you.
Can you
What?
hear me?
Now I can, yeah.
Can you hear me?
Yeah.
Okay. I have 53.6.
No, impossible.
Okay, because I just added them. I think I did the same thing Alexis did because I was having similar issues.
Okay. Okay, hang on. It's okay. Emma.
Okay, I got 14.8,
Uh-huh.
8.6,
Uh-huh.
7.6,
Uh-huh.
12.4,
Uh-huh.
and 9.2.
Okay, interesting. Okay, Reina. Okay, Sylvia.
Okay, I had 17,
Okay.
14.8,
Uh-huh.
14.4,
Uh-huh.
14.6,
Uh-huh.
and 18.4.
Okay. And Imani. Can't hear you.
Can you hear me?
Now we can, yeah.
I have 15.2,
Uh-huh.
13.4,
Uh-huh.
11.8,
Uh-huh.
13,
Uh-huh.
and 9.2.
9.2. Okay. All right. So this is very interesting. First of all, can everybody see that there's a lot less variability when I have a sample size of 5 than really what this was a sample size of 1, because it was every single penny. Juliana, you got something? Talk.
I fixed it. I added up the wrong numbers. I didn't add the years. I added up the pennies.
Okay,
So,
what do you
want
got?
me to say them?
Yeah.
So I got 11.8,
Uh-huh.
10,
Uh-huh.
5, 9.2,
Uh-huh.
and 12.
12. Very good. Okay, thank you. That makes it even look a little. Alexis, did you do it over?
Yeah, I figured it out. It like when I added it, I didn't put it like in parentheses, so it was just like dividing the last
Just
number.
dividing the last number. Yeah, okay.
So I had 14.2,
Uh-huh.
14.6, 13, 16, and then 24.8.
Oh, wow, that one's way over here. There's an outlier there, I think, huh?
Yeah.
All right. So a lot more variability here than here with our sample size of 5, right? Everybody see that? Less variability. Are you clear on that? Yes. And what else do you notice?
It looks like the first graph, like it's skewed to the, well, actually, it's not really skewed to the right, but
No, I don't think so, especially if we eliminate Alexis's outlier.
yeah, true.
Yeah, I think I think we're looking at unimodal and symmetric here. Yeah. Yeah. And the center looks to be pretty close to the center that they gave us of 12. So this is interesting. This is a good like simulation that we're doing on our own right here. So what we're going to do when we come back on, so keep your numbers, okay? Keep your numbers, because when we come back on Thursday, look on the right way. We are going to do it with adding up all of our means and then taking the mean of those. So it's like taking the mean of a sample of 25. So we're going to do it. We're going to have it with even a larger sample. So we're kind of like really experiencing what happens with larger the sample size, the less variability, and the mean being actually what the population mean is. All right, so 11:10. What do we got going on here now? Break. Next class 11:30. All right. Goodbye. See you later.
Thank you.
Thank
Thank
you.
you.
Thank you.
You're welcome.